So here is lemma 5. Let AN converge strongly to A and BN converge strongly to B. We will worry about the spaces when we need them. Then, before we can state and prove that the limit of the product is the product of the limits, we need a little lemma inside the lemma A. A strongly convergent sequence is bounded, which of course means the sequence of norms is a bounded sequence in the real numbers, so it has a supremum that is finite. And of course this will also hold for the sequence Bn, but I guess it's enough to say it for one sequence. If one sequence is strongly convergent, then it is bounded. And we kind of remember this statement from convergent sequences in metric spaces, and hence in particular for the case when this was uniform convergence. But it's good to know that it still holds when we weaken this down to strong convergence. But now, unlike in the setting of uniform convergence, this is a much less obvious statement. And in the proof, we will not give a full proof. We will just say that this is the Banach-Steinhaus theorem. And the fact that it has its own name and that Banach even needed the help of a friend to prove it kind of indicates that this is not something that we could do here with bare hands. By the way, Hugo Steinhaus was the mathematical mentor of Stefan Banach, and when Steinhaus was asked about his most important mathematical discovery, he answered Stefan Banach. Okay, but before we are losing focus here, let's continue with what we actually want to prove, and that's this statement here. So the product of our two convergent operator sequences is again convergent, and the limit is the product of the limits. But before we prove this, let's state the same result for addition instead of composition, just for completeness and because it's easy to do. Okay, so here we have statements B and C. Right, let's prove B. And to show the strong convergence here, you have to apply both AN plus BN and A plus B to the same vector X, and then look at the difference and show that the norm of this goes to 0 for all vectors X from the space where both A and B, and as well AN and BN, are starting from. Okay, but like I said, this is really easy. You just have to recall what the sum of two operators is doing with an element. Same here. Okay, and then to continue. And if you rearrange these terms, so getting the AX with a minus in front next to the AX and the BX with a minus in front next to the BNX, you arrive here. Okay, and then simply by triangle inequality, you squeeze norm signs in here and turn this into a less than or equal to. And by convergence of AN to A, we can see that this goes to 0, and similarly by convergence of BN to B, this goes to 0, and hence the sum goes to 0 for every X in that space. Okay, for statement C, which we are actually after, spaces have to be a little bit different. So A has to start where B is ending, because you have to read this from right to left, you know. And we now have to look at this expression for all little x's in the space where B is starting. And to make some progress here, you need the same trick that you've been using in your Analysis 1 course when A and B were still real numbers and written in lowercase. And by the way, this is the same trick that was also helping in problem 4C. And let me just quickly sketch that trick here. I mean, it's not rocket science. So you have your two sequences, AN goes to A and BN goes to B. But now you're looking at products AN, BN and AB. And you're looking for an argument that brings you from here to here across the diagonal in this little diagram here. And because you know that you have convergence as long as you go in this horizontal or in this vertical direction, the trick is to go first to the side and then down, or possibly the other direction, but you have to go around the corner. Well, let's try it with this corner here. So what I mean is that this is the same as first going from AN, BN, x down to AN, BX before you start again at that point and go to your final destination ABX. So I think nobody can argue with that equality sign because all we're doing here is adding a 0. So let's copy that last line and use triangle inequality by splitting this here and here, which turns this into a less than or equal sign. And now let's see what we can do. Well, here we can factor AN out to the left. And here we have the same vector bx twice. So let's just relabel that as little y, which is coming from the space where b is ending and a is beginning. Okay, and then in the first term we can get the norm of AN out, which is again an inequality, but in the same direction here. And in the second term, let's just replace bx by y. And then we all agree that we are pretty much on the finish line, because by strong convergence of AN to A, this goes to 0. By strong convergence of BN to B, that goes to 0. And, now this is the key, by Banach-Steinhaus, this here is bounded. Okay, and then if you take a bounded sequence, multiply by a null sequence, you get a null sequence. And then the sum of two null sequences is a null sequence as n goes to infinity. And that's your proof via the walking around the corner trick, if you even want to call it a trick. Okay, so why did we do all this? Well, just to be able to tick this argument and therefore that question. Okay, so remember, we can now argue that the product of two or more sequences by just iterating the argument from lemma 5c converges, and the limit is just the product of the two or more limits. Okay, so that's what projection methods look like, and yes, they are approximation methods. So let's write this down in a definition. A projection method for an operator A from x to y is an operator sequence AN, where AN is of the particular form Pn hat A Pn. Well, you know that when we evaluate that, we read it from right to left, with projectors Pn converging strongly to the identity on X, and Pn hat, also a projector, converging strongly to the identity on Y. Can you see how our discussion about projections is paying off here? It just takes us 2 seconds to write projector. And let me make one more comment here. So when we kind of constructed these projection methods, we said that our projectors Pn brings us down to the subspace Xn, and Pn hat brings us down to the subspace Yn, which are the images of Pn and Pn hat respectively. And when we first spoke about approximation methods, we said that from a numerical perspective, we want to work with something finite dimensional. So we typically think of finite dimensional subspaces Xn and Yn here, even though we didn't say that in this whole definition, but of course it's not forbidden to choose them finite dimensional. But if you do so, then you want to make sure that they all have the same dimension, because your operators an that we're looking at here are now operators that bring you from xn into yn, and in the end you want them to be invertible, right? So for applicability, stability, you're going to talk about the inverse of these operators an as operators acting between the subspaces xn and yn. And if these are finite dimensional, you can think of an as a finite matrix. But before you can talk about invertibility of that matrix, it has to have, of course, same number of rows and columns. So dimension of xn and dimension of yn should better be the same if you want to invert these operators here. Let's make a note of this last comment here below our definition, because this is quite important.